Can you believe it? When you are driving an electric car, the moment you step on the brakes going downhill or at a red light, the current generated by the reverse rotation of the motor might actually be several times larger than the current from the charging station you plug in at home. Many people think the charging station is the only monster pumping electricity into the battery. But in fact, the brake pedals under your feet might just be an invisible, ultra-high-power supercharging station. This sounds incredibly counterintuitive, right? We are clearly consuming the car's kinetic energy. So how can the current flooding into the battery are more intense than the dedicated charging equipment we connect? Today, we are going to do a hardcore teardown of an EV's regenerative braking system to see just how much current it can squeeze out in an instant. Can it really be larger than an external charging station? The physical and engineering truth behind it will absolutely subvert your existing imagination. In this video, I'll break it down into several core sections to dive deep with you all. First, we'll start with a hardcore physics and electrical engineering lesson to understand the underlying logic of regenerative braking and see how the motor in your car, in fractions of a second, turns from a power-consuming monster into a power-generating behemoth. And what kind of magician's role does the inverter play in this? Next, we will enter the most exciting data showdown. I'll directly take you through the physics formulas, taking the peak power and current generated at the moment of hard braking, and compare it with our common household AC slow chargers, as well as the ridiculously expensive outdoor DC super fast chargers, for a head-to-head ultimate comparison. Then we will dive into the deep waters of battery protection. From an electrochemical perspective, when such a fierce braking current is instantly poured in, can the battery really handle it? And how does the BMS battery management system behind the scenes come to the rescue? Finally, I will also share with you why sometimes you feel that the brakes on an EV are a bit soft and what intricate relationships this has with the massive current we are discussing today. First, we need to break a myth, and that is the word charging. In traditional concepts, charging means taking a bulky connector and plugging it into the car's charging port, and then watching the numbers on the screen slowly tick up. But from the perspective of physics and electrical engineering, as long as there is a current with a voltage higher than the battery's current voltage flowing backwards into the battery pack, this process is called charging. And on an electric vehicle, the thing that can do this, besides the external power grid, is the driving motor on your car. When we step on the accelerator pedal, the battery outputs DC power, which goes through the car's inverter, which is what we commonly call the inverter, to convert the DC power into three-phase AC power, driving the motor to generate forward torque, pushing the car forward. This is the process of converting electrical energy into kinetic energy. However, when you release the accelerator, or when you step on the brake pedal, the entire physical world instantly reverses. At this time, because your car has mass, combined with its moving speed, it carries a massive amount of kinetic energy. Your motor was originally outputting power, but now because the wheels are still turning, the wheels, through the drive shaft, inversely drive the motor's rotor to continue spinning. Everyone learned Faraday's law of electromagnetic induction in middle school physics. When there is relative motion between a magnetic field and a coil, an induced electromotive force is generated. That's right, at this moment, that permanent magnet synchronous motor with hundreds of horsepower on your car, or induction motor, instantly becomes a super large generator. The three-phase AC power it generates will pass through that inverter again. Only this time, the power semiconductor components inside the inverter, whether it's traditional IGBTs or the latest silicon carbide SiC modules, their role changes to that of a rectifier, responsible for rectifying this violent AC power back into DC power, and then fiercely pumping it back into the battery pack. This process of converting kinetic energy back into electrical energy is what we call regenerative braking, also known as regenerative braking. After understanding this mechanism, we are going to enter today's main event. Just how much electricity does this regenerative braking generate? Can it compare to a charging station? To compare this, we must first clarify the strength of our opponents. Let's first look at opponent number one, the household AC slow charger. The charging stations we usually install in our home garages are typically single-phase 220-volt AC power. The common power is about 7 kilowatts, or 7 kilowatts. How do we get this 7 kilowatts? The formula is simple. Power equals voltage multiplied by current. 220 volts multiplied by 32 amps of current is roughly 7 kilowatts. That is to say, while you are comfortably sleeping at home. The charging station is steadily charging your car at a current of about 32 amps. If your onboard charger OBC is more advanced and can support up to 11 kilowatts of three-phase AC power, then the current is about 16 amps per phase. Remember these numbers. The current of a household's flow charger is roughly in the range of 16 to 32 amps. Next, let's look at opponent number 2, the DC Supercharger. When you are running out of power on the highway, pull into a resting area and plug in the Supercharger gun. That is an entirely different realm. Mainstream DC fast charging stations today, ranging from 150 kilowatts to 250 kilowatts, and even up to the latest 350 kilowatts. Taking a 250 kilowatt supercharging station as an example, if your car uses a traditional 400-volt architecture to achieve a power of 250 kilowatts, let's calculate using the formula 250,000 watts divided by 400 volts. The current reaches a staggering 625 amps. This is a very terrifying number. This is also why the cables at supercharging stations must have liquid cooling circulating inside them to dissipate heat. Otherwise, with such a massive current passing through, the wires would immediately melt and catch fire. Okay, now we have two reference points: the 32 amps of a household's flow charger and the 600 amps of a DC supercharger. Now, let's turn our attention back to our protagonist, the brake pedal. When you are driving a 2-ton electric car, speeding down the highway at 100 kilometers per hour, and debris suddenly appears ahead, causing you to slam on the brakes. At this moment, massive kinetic energy must return to zero in just 2 or 3 seconds. According to the kinetic energy formula, kinetic energy equals 1/2 times mass times velocity squared. For a 2-ton car traveling at 100 kilometers per hour, the contained kinetic energy is approximately 770,000 joules. If we require that within 3 seconds, all this energy is recovered and converted into electricity via the motor. Then the instantaneous generating power would be as high as over 200 kilowatts. Of course, in the real world, the conversion efficiency of the motor and inverter is not 100%. And when braking hard, traditional hydraulic calipers will also intervene to help decelerate through friction. So the kinetic energy 1T entirely turned into electricity. But even so, in many electric vehicle system settings, the peak power for regenerative braking, it is very commonly set between 60 kilowatts and 100 kilowatts. Let's take a median value. Assuming the moment you hit the brakes hard, the motor generates 80 kilowatts of recovery power. If your beloved car is a common 400-volt architecture electric vehicle, 80,000 watts divided by 400 volts yields an instantaneous current as high as 200 amps. Look, there's the answer. The 200 amps of regenerative braking current completely crushes the 32 amps of a household AC charging station, being a full 6 times larger than a household charger. This is why I said at the very beginning that the brake pedal under your foot is an invisible super fast charging station. When you are enjoying the thrill of continuous downhills on a mountain road, with every heavy brake before entering a corner, your battery is enduring a massive current, far greater than when it's plugged into your charging station at home at night. However, if we switch the opponent to a top-tier DC super fast charging station, then regenerative braking is still slightly inferior. We just calculated that a 250 kilowatt supercharger can deliver over 600 amps of current. This is much larger than the 200 amps from typical vehicle regenerative braking. Only in some extreme performance electric sports cars, such as models equipped with 800 volts or even higher voltage systems, where their motor power is immense, can the instantaneous power of regenerative braking even exceeds 250 kilowatts to 300 kilowatts. Only then is the recovery current likely to briefly rival DC fast charging. But in summary, the current from regenerative braking is absolutely larger than AC slow charging and usually smaller than top-tier DC fast charging. Now the question comes, as those with an engineering mindset, we must wonder, can the battery handle it? We all know from normally using our phones that fast charging makes the battery heat up and damages it. Now, with currents of 200 amps easily being instantly poured in, will the battery just straight up explode? This involves a very critical concept in battery science, the charge and discharge C rate, which is what we commonly call the C rate. The discharging and charging capabilities of a battery are completely asymmetrical in their physical chemistry mechanisms. During discharging, lithium ions deintercalated from the graphite layer of the anode, pass through the electrolyte, and swim to the cathode. This process is relatively easy, like people running out of a crowded building. As long as the door is big enough, everyone can run out quickly. So when an electric vehicle is accelerating at full throttle, the battery can instantly release hundreds or even thousands of amps of current. This is called high C-rate discharging. For modern motive lithium batteries, this is almost basic capability. However, the situation is the complete opposite during charging. Charging is lithium ions starting from the cathode, swimming back to the anode, and precisely intercalating into the layered structure of graphite. This is like thousands of people trying to squeeze into a building all at once, and every person has to find their own seat and sit down. If the charging current is too large, meaning too many people are entering too quickly, these lithium ions will cause a traffic jam on the surface of the graphite anode. Even scarier, if they can't get into the graphite layers, they will accumulate on the anode surface and reduce into metallic lithium. This phenomenon has a terrifying name in battery engineering. It's called lithium plating. Lithium plating is extremely fatal. This metallic lithium will slowly grow into dendritic crystals, which we call lithium dendrites. When these sharp dendrites grow longer and longer, and eventually pierce the separator dividing the anode and cathode, it will cause an internal short circuit in the battery, instantly generating ultra-high temperatures. This is one of the most fundamental chemical causes of electric vehicle fires. Since high current charging is so dangerous, then why can our cars still withstand the fierce 200 amp current during the moment of braking? There are two key guardian angels here. The first guardian angel is time. When we step on the brakes, that extreme high power and large current usually only lasts for a very short period of time, maybe only 1 or 2 seconds. As the vehicle's speed drops rapidly, the motor's speed decreases, and the generating power will also plummet like falling off a cliff. Although this short pulsed current has a large amperage, the total energy is not much. Before it has time to trigger a severe lithium plating traffic jam on the anode surface, the current has already dropped. This is completely different from the situation where you are continuously pumping hundreds of amps at a supercharger for half an hour. The second guardian angel, and also the most important line of defense, is your car's BMS battery management system. The BMS is like the super brain and security system of the battery pack. It monitors the voltage of every single cell around the clock, as well as the temperature and the current state of charge stock. The BMS is filled with various complex algorithms and limit curves. When you step on the brakes, before the motor is about to pour massive current back into the battery, the inverter must first ask for the BMS's permission. The BMS will strictly evaluate the current situation. If conditions allow, it will let this massive current pass. But in a few scenarios, the BMS will mercilessly shut the door, limiting or even completely refusing the entry of regenerative braking currents. The first scenario is when the battery is already very fully charged. When your sock reaches 95% or even 100% full charge, the inside of the battery is like a train car that is already packed with people. At this point, even if just a little bit of regenerative braking current tries to squeeze in, it is very easy to trigger a lithium plating reaction because there are simply no empty seats left. So when you just fully charged and drove the car out, and you release the accelerator at the first traffic light, you will suddenly realize, why isn't the car decelerating? Where did that usual strong pulling sensation go? It's not that your car is broken, but that the BMS detected the battery is full. In order to protect the battery from being overstuffed, it directly limits the regenerative braking power to a near zero state. At this time, the motor will not become a generator, and the car will just coast like a traditional gas car in neutral. The second scenario is when the battery temperature is very low. In the cold winter, the electrolyte inside the battery will become very viscous, and the activity of lithium ions will drop significantly. This is like half of the building's entrance being frozen shut, making everyone move sluggishly. If you forcefully pump in a large current in this low-temperature state, lithium ions won't have time to swim to the anode, which will absolutely lead to severe lithium plating. Therefore, during a cold start in the winter, the BMS will also drastically limit the force of regenerative braking. You must drive for a while to let the battery's internal heating system or its own discharging warm the battery up to a suitable operating temperature. before the pulling sensation of regenerative braking will slowly return to normal. Hearing this, you might feel a bit terrified. If my car is just fully charged, or if I just hit the road in winter and regenerative braking is turned off, then if I hit the brakes in an emergency, won't the car be unable to stop? Please rest assured, automotive engineers thought of this problem long ago. Modern electric vehicles are equipped with highly advanced brake blending technology, namely the CRBS Cooperative Regenerative Braking System. This system decouples travel from your brake pedal, the actual deceleration. When you step on the brake pedal, you are actually just sending an electronic signal to the car's computer, stating how much deceleration I need. After receiving the signal, the computer will prioritize calculating how much braking force regenerative braking can currently provide. If the regenerative braking force is sufficient, the calipers won't clamp down, and it relies entirely on the motor generating electricity to brake. But if, as we just said, the battery is full or too cold, and the BMS rejects regenerative braking, the computer will immediately and seamlessly take over. Start the hydraulic pump, push the brake calipers, and use traditional brake pads to rub against the brake discs to bring the car to a stop. This switching process is very rapid and smooth. Most drivers can't feel at all whether it's the motor braking right now or the calipers braking. You will only feel that the car has come to a steady stop according to your will. However, there are also some early or less well-designed electric vehicles where this blending system is not refined enough. In a fully charged state, regenerative braking suddenly disappears, but hydraulic braking doesn't step in with the same force in time, which causes the driver to step on the brakes, yet feel the illusion that the car is still rushing forward. This is the terrifying experience of spongy brakes, or brake failure that people often talk about. This is actually a software tuning and system integration issue, not that the hardware is genuinely broken. In summary, an electric vehicle's brake pedal is indeed an uncompromising instantaneous large current generator. In your daily driving, with every deceleration, the motor is using a current several times that of a home charger to desperately stuff energy back into the battery, helping you increase your driving range. Modern battery technology and smart BMS management systems can already perfectly master this instantaneous large pulsed current to ensure the health and safety of the battery. Next time when you are carrying a friend and smoothly decelerating on a downhill stretch using regenerative braking, you might as well proudly tell them, did you know? Right now, we are using a current several times fiercer than our charging station at home. To crazily charge this car,